talked about the history of submarines, but we haven't really talked about what submarines have got heading for them in the future. Submarines are looking to be improved in a couple of different areas, specifically the following four. The first of which is to go to greater depths of the ocean. So submarines are limited in how deep they can dive because they are because the ocean gets very, very high pressure very quickly. So there's only so far that most submarines can go, but we're working on new materials, new designs, that will allow submarines to go further and deeper than ever before. Or the weapon? What do you mean? You mean submarine weapons or just... Because I will be going over torpedoes a little bit later in the class today. We're also trying to get submarines to navigate more effectively. They're still a little bit clunky to navigate, and we are limited by the fact that submarines are underwater, and most of the signals that they use to navigate are found in the air. Obviously, submarines can surface to navigate, but that's not always what we're looking to do. We sometimes want to be covert. So they're trying to figure out more ways to navigate the submarine more effectively, as well as using more powerful weapons. Now, I don't really like this one because we already have nuclear torpedoes. I don't think we've ever fired one before. Anybody, at least against somebody else. But I don't think that I personally want to find more powerful weapons. But I guess navies, armies, whoever are looking for that are interested in that. And finally, more effective remote controls. That's very similar to the navigating more effectively. Remote controls are only so sensitive at this point. So the more sensitive the remote controller gets, the more data that we can take underneath the ocean, the more precise we can be when we're taking data or samples or whatever it may be. So that's what we're looking at in the future here. And there we go. Let's talk about some submersibles, which are like little tiny submarines that can only fit maybe a person or two in there. So on the right here, there is a submersible called Alvin. This is probably the world's most famous submersible. Does anybody have any idea what it's been used for? It's okay if not. It's obviously a submersible. It goes very deep under the water. Yeah, it is for exploration, but there's a certain shipwreck that has been explored, probably the most famous shipwreck of all time. Yep, Mateo got it. As did Hannah, the Titanic. So, Alvin is a kind of submersible, which is a submarine that's used for exploration and can only go a limited depth underwater, or though it will be crushed by the force of water pressure. So Alvin was piloted by this director, James Cameron, who ended up, oh my goodness, I'll answer that in a second, who ended up funding an endeavor to go see the actual shipwreck of the Titanic. And the Alvin here is what he used to do that. And that's where all the footage that you see in the movie Titanic comes from, of the Titanic underwater. So, submersibles are usually used single person use for exploration, not so much for warfare. So, oh my goodness, what's happening here? Yeah, what did you just do, Mateo? You just copy-pasted like everything that we've said in the chat box. And you're fine, Elijah, no worries about being late. We're just talking about some more submarine stuff. But, okay, well, I don't know what that was, but it's okay. Um, so, submersibles and submarines, even though they have different functions, submersibles being single person or two people exploratory vehicles, submarines being more for warfare in general. Both of these have to have certain systems to sustain life underwater. We can't just have, people hanging out without the ability to breathe or anything. That's not a very good prognosis for the people in the submarine. So to support life, submersibles must take into consideration the following three life support activities, which is first, maintaining air quality, second, maintaining a fresh water supply, and third, maintaining life-sustainable temperature. So let's go a little bit further into that. The first being maintaining air quality. Obviously, submarines are underwater. There's not much air underwater. That's not a surprise. How they get air underwater, though, first specifically is talking about replenishing oxygen. There is a process called electrolysis, which is a chemical reaction that converts water, which is good old H2O, into two different gases. H2, which is hydrogen gas, and oxygen, or O2, which is oxygen, which we breathe. I'm not entirely sure what they do with the H2, because the H2 is very dangerous and flammable, but the oxygen is obviously makes up 21% of the atmosphere. It's what we breathe a whole lot of. So we're looking to maintain an atmosphere very similar to what we're looking at on Earth, or on land rather. And so electrolysis is how they do it underwater. So to keep the air quality good, we also must remove carbon dioxide, which is the gas that occurs when we exhale. And the material that they use to remove carbon dioxide is called soda lime. Now, it's not like Sprite, it's not lime soda or anything. It's actually a chemical which is called soda lime, which reacts with carbon dioxide and sort of removes it from the air. So we have to make oxygen, we have to remove the negative effects of breathing. And finally, we have to remove excess moisture. Now, most of you are probably in North Carolina right now, and we're familiar with how humid it gets in the summer. Humidity is basically just how much moisture is in the air, and in the summer we get to about 100% humidity, meaning that there's a whole lot of moisture in the air. So a dehumidifier is used on submarines to take a lot of the moisture out and make it a lot more pleasant for the people on the sub. So maintaining air quality is number one. Number two, to keep people alive, we got to maintain a fresh water supply. So we use a distillation process in submarines, which basically you turn water into steam, and when you do that, all the chemicals that have dissolved into water get left behind, while the steam, which is made of only water, gets put into sort of a separate tank and gets condensed into normal drinking water. So, obviously, ocean is very salty. Even though we have water aplenty, we need to get the salt out of the water, and that's how we do it. And in nuclear subs, the steam that is generated by nuclear reactors can be distilled into fresh drinking water. And there's a lot of water that's required on subs. So depending on how many people are on the sub, depending on the sub itself, between 38,000 liters to 150,000 liters of fresh water are needed per day. So that's for, drinking, cooking, showering, whatever it may be. So that's a lot of water. But luckily the nuclear reactor, which is powering all of this, can do a lot of that for us. I'm not sure specifically how gas-powered submarines do that, but it's a question for another time, I guess. But also, the freshwater supply does cool down the submarine some and keeps the crew comfortable. Now, the submarine is in an interesting state between really hot because the nuclear reactor is very hot and just that's inherently, and the deep sea, which is very, very cold. And that brings us to our third point here, maintaining temperature. So we're not trying to freeze our sailor guys to death, but we're also not trying to melt them. So at least in a nuclear submarine, the electrical generators heat the sub to a very, very warm, and I'm kidding about that, 38 degrees Fahrenheit. So while that's chilly, you can survive that. It's not pleasant, but you can definitely survive that. Okay. So that's what people need to contend with when they're making a submarine habitable. So at this point, we can talk a little bit more about how a submarine works in terms of buoyancy. We talked about buoyancy a little bit, or we watched a video by the sea perch people about how buoyancy works. So let's talk a little bit more in depth about that. So buoyancy is an upward force that keeps things floating. It's determined by two things: the weight of an object in the water and the weight of the water that it displaces. So when you put an object into water, the water around it has to move to accommodate the object. Does that make sense? And if the object displaces the same amount of weight of water that the object weighs, the object is called neutrally buoyant. So it's basically going to be hovering in the water. So, where's it going with that? Basically, this is what we're looking for our sea perch to do. We want our sea perch to not float, not sink, but we want to weight it so that it just sort of hovers in the water, so it can go flying around, so it won't just be a sort of sinking boat or an object just crawling along the ground of the pool. We're looking for displaced water, weight, and the object to be roughly the same here. And it's kind of hard to visualize, but I'll give you a couple examples in just a minute on how that works. And similarly, if the weight of the object is more than the weight of the water the object displaces, it is negatively buoyant or not buoyant, and the object will sink. The opposite of that, the weight of the object being less than the weight of the water it displaces, makes an object buoyant, which means it'll float. So it's still kind of hard to visualize. So let's take a look at a classical example of buoyancy here. And I do see a question before I do that. You just got here, so you'll go and watch the YouTube video later. Alright, awesome, I appreciate that. You didn't miss too much, but definitely the first 15 minutes of class you can rewatch. Has anybody ever heard of a Cartesian diver before? Probably not. I'm just seeing if maybe one of your science classes has shown it. No? And okay, I'm going to show you how it works in just a second. So basically, it is a very simple experiment that you can do at home to examine the effects of buoyancy, as well as the effects of pressure, but I'll show you that in a second. It was named after René Descartes, who is said to have built the first one as like a children's toy. So I'm going to show you part of a video to show you how it works, and then we will discuss it afterwards. You don't really have to listen, you just need to watch. So if you can't hear, don't worry. Obviously our safety goggles there. And you can make this at home too, so don't, if you're confused, you can definitely watch it on your own. So you're filling a bottle of water, putting an eyedropper into the water, and filling it up, so that it's just barely floating in the water, just like it is right there. You'll put the eyedropper in the water, top the bottle off, and close the cap. that the eyedropper sinks once you've squeezed it. When you unsqueeze it, the eyedropper floats back up. And apparently if you knock it over, you'll have to start over again. But the basic process here, you have a eyedropper in some water, squeeze the bottle, eyedropper sinks, unsqueeze it, eyedropper floats. So let's talk a little bit more about that. So the first thing that you have to think about is how the eyedropper starts. At the start, was the eyedropper positively, negatively, or neutrally buoyant? So go ahead, call it out. Anybody. If you need to see which one each is, I'll go back to the slides that show that. Okay, I see a good answer here. The object is floating, so it's going to be positively buoyant. Alright. So it is not quite entirely positively buoyant. It's a little bit neutral since it's not totally floating at the top. But basically what this means is at first, the weight of the object is less than the weight of the water it displaces. So that air bubble does make a big difference. Now let's think a little bit more about what else happens in that video. The eyedropper sinks when the bottle is squeezed. Now why would it sink when it was just floating? What did we do to change the eyedropper's state? How did we make that guy sink? What do we do to the water bottle? We didn't do much to it. We literally just... Alright, Josiah knows what's going on. We literally just squeezed the water bottle. That made it sink. And so Josiah had a good point here. That it has to do with high water pressure. It's exactly right. Squeezing this bottle increases the pressure of the water. In turn, this increases the pressure of the air inside of the diver. So you'll have to consider the fact that air is what we call a compressible substance, meaning that you can compress it into a lot smaller volume just by applying pressure to all sides of it. So that's why we have compressed air tanks, for example. So you can squeeze air into a lot smaller space, but water is not compressible. You can't get water and squeeze it into a tinier area, or a tinier volume, sorry. The water's volume stays the same. Let me start over again, sorry. When we squeeze the bottle, the air pressure increases, which makes the area of the air smaller. To take place of this air, the water will come into the eyedropper, just to replace the volume of the air. Because there's more water inside of the dropper, I'll go to the next slide, this increases the weight of the eyedropper. So what happens is the weight of the object starts to exceed the weight of the water it displaces, meaning that it's negatively buoyant, and you got it, it sinks. Now the reverse happens when you stop squeezing it. The air is allowed to return to its initial volume, so it floats again. So you can do this over and over and over again, just float, sink, float, sink, float, sink, float, sink. So what I want you to take from this, other than the cool stuff about pressure, is that adding air to an object generally makes it float, because air is lighter than water. in a density sense, rather. So let's apply that to real life. Let's talk about scuba divers before we get to submarine buoyancy here. So scuba divers have to compensate for buoyancy by using weights and buoyancy control devices. Now, it's not a device like a machine or anything. One type of buoyancy control device is just the diver's breath. Filling the diver's lungs fully with air is going to make the diver ascend. So you're going to start floating towards the surface. And when you empty your lungs as a diver, you don't have this air to keep you sort of floating up, and so you sink. Scuba divers learn to breathe so that they stay fairly neutrally buoyant. They also learn what weights they want. It's a little bit more complex than that, but that's the very big baseline of it. I had a student that told me last class that they are on the swim team, and their coach recommends that when they first dive in, to completely exhale so that they can go farther underwater at the beginning of their races. So think of it like that. If you're going to dive into a pool, if you dive with a full lung of air, you're not going to go as far. Make sense, y'all? So let's bring this back over to submarines. Submarines use it a little bit differently, but similar concept here. It's true, but it's harder. What do you mean? While you articulate that thought, oh, to completely exhale? Oh yeah, most definitely. It's not very easy to completely exhale. You're going to want to have some air in your lungs, especially if you're going underwater, but to the most extent, you would want to exhale completely, as much as you can. So submarines have sort of what they call ballast tanks on the outside of it. A ballast tank is something that can fill with air or water to make it sink or float. So to sink, all a submarine has to do is open a valve. Submarines' ballast tanks rather, will fill with water and make it sink. The best thing to do is to hum. Huh, that's good to know. Thank you. So we're filling the ballast tanks up with water, pulling that submarine down. Now to surface your submarine, compressed air, remember air is compressible, is released into the ballast tank. Compressed air is at a much higher pressure than the seawater, and so it's going to empty all of the water out of your ballast tanks. So all of this water gets displaced back into the ocean. The air is going to make your sub rise, and once everything is, all the water's out, you have surfaced. So we're just making our sub negatively buoyant by adding water into the ballast tanks, and then positively buoyant by using high pressure condensed air to remove the water. And that's it. I think it's pretty cool stuff. So any questions on buoyancy, because that's probably one of the most important things that we will discuss in terms of your sea perch? You got questions? Shoot 'em. once you get that thought out, I'm going to run a poll just to see if I'm going too fast or too slow for today. Still got a lot of material to cover, and I think you'll keep enjoying it. Actually, let's go ahead and run it now. Let's see how my pacing is going. I get one more person to vote who hasn't voted yet before I continue. Alright. Alright, perfect. So it looks like I'm keeping you on the same page. It's alright. So, now that we've discussed buoyancy, we're going to talk about nuclear subs and nuclear reactors. So, like I said, nuclear subs have a nuclear reactor in them. Nuclear reactors work on nuclear fission to turn a steam turbine. Now, before I go more into that, I'm also going to say that gears, which make turbines turn basically not as fast, take the mechanical energy and convert it into electrical energy by using a generator. Now, I'm going to show you a video that is a little bit more in depth about that, and then I will go more into depth about this. So the question here is, how come the sea perch can float with all the motors and stuff? Well, that's the deal. You actually have to make your sea perch neutrally buoyant. So we're going to be drilling holes into your sea perch so it can fill with water. And unlike with submarines, which have ballast tanks, we're actually going to use a motor to push this up or down. So the sea perch can basically float because your motor is applying a force upward so that it floats. It's a little bit different than an actual submarine. But with all the motors and stuff on it, your ultimate goal is to, without motors or anything on it, just make it float neutrally. To do that, you use weights or floats. So if it's sinking, add some floats. If it's floating, add some weights. And it's trial and error to get that. It's just something that we'll do in lab, and I'll show you when we get to that point. So let's talk about how a nuclear power plant works. Again, you don't really have to listen to it, you just sort of need to watch it. Excuse me. So let's watch this guy here. And I'll pause it a couple times to talk. So, nuclear power plants use uranium rods, basically, a whole bunch of them close together, which we call a nuclear reactor core. So in these rods, neutrons are fired initially. So let me go back just a second real quick. Particles are fired at these atoms, which basically will split when the particle hits it, releasing more particles, which basically makes a chain reaction happen. There we go. Radiation is released in the form of heat, and we'll continue to watch this from here. So, chain reaction going on. Nuclear reactors normally have a like a cooling tank, which I'll explain in a second, but the heat that the nuclear reactor core creates makes steam when in contact with water. The steam is pressurized, and it goes into a turbine, which is basically just a big old fan, and it makes the fan turn. So that converts this heat into mechanical energy. After it goes to the turbine, what will happen is the steam, which is in a gaseous state, will then condense back into a liquid state by cooling. So we're going to cool down this steam to make it fresh water. Remember distillation? That's what's happening here. This fresh water is then pumped back into the reactor to repeat the process. So that's just the very, very baseline of not even a nuclear submarine, but a nuclear reactor in general. So it's a little bit more complex when it comes to a nuclear submarine. The turbine will turn and power an engine. The hot air after it goes to the turbine will actually go into the condenser, which is cooled by seawater. Remember, the seawater is real cold. This condensed water will be pumped back into the steam generator, and this cycle will occur simultaneously to this cycle. Now this cycle, what's happening, again, chain reaction going on with the neutrons, and I'll explain specifically in a second. It gets pressurized extra just so it goes into the steam generator. The hot steam here will heat the water in the steam generator, which generates steam. It does exactly what its name says. After the energy is lost to the water in the steam generator, the water within the reactor will be pumped back into the reactor. Now it's important to note, when it comes to nuclear submarines, obviously people are real close to these nuclear reactors. Radiation's a little bit dangerous. So there are actually two shields around the reactor. So one around the uranium cores itself, and one around the system that is directly related to the nuclear reactor. So the reactor compartment is separate from the engine room. The engine room should not have any contact with any radiation, so it is safe to work in there for the sailors. So nuclear submarines can stay submerged for almost a week straight without going to surface, and are only limited to surfacing by their supply of food. If you don't have enough food, you're not going to have a good time. So the chain reaction that's produced by the reactors, again a particle, in this case a neutron, collides with a uranium atom, which releases heat and more neutrons, 3 specifically, and the reaction goes on and on and on and on and on. And actually, the cooling pool that I mentioned earlier during the video, we use that cooling pool so that the reaction is limited in how much energy it can produce. Anybody know what it's called when a nuclear reactor isn't sufficiently cooled? It's something that y'all know. If the chain reaction's allowed to go uncontrolled, you do call it bad. Specifically, Mateo got it, we call it a meltdown. So that's what happened in, it happened in Chernobyl, happened in Fukushima, well sort of, a little bit different in Fukushima, but a nuclear meltdown is what we call it. So I'm going to get even more specific about how this works now. I don't expect you to fully understand this because a lot of nuclear chemistry, which is weird, to say the least. But nuclear fission, again, which is what causes all this stuff here, starts with a loose neutron, and it might come from an initial power or initial particle source, or even another atom, collides with a uranium atom. This neutron becomes part of the uranium atom, and it becomes unstable. It decays into 2 different elements. So we got krypton, and we've got barium. So they splits into these 2 particles. It emits heat in terms of gamma radiation, and then it emits these 3 neutrons here. So that's specifically how all this stuff is working. So I think it's pretty cool. So that's all I've got about nuclear stuff. We're now going to talk about the navigation systems of submarines. They've got a couple different ones. Submarines don't have any windows. usually. They might have one porthole, but if you were going to look outside anyway underwater, you're only going to see maybe some fish, maybe some dark water. That's about it. So the question, before I continue, is how do you get a uranium atom? Uranium is mined. It's in a state that isn't quite as radioactive, and through some sort of purification process, we get their uranium that we used in fission, or in uranium cores. I don't know specifically how they purify it, to be completely honest, but what's cool about uranium is that in nuclear power plants, you only purify it to about 3% pure. So not very high. Nuclear power is very, very safe overall, unless a meltdown happens. But for nuclear weapons, any idea on a number how pure the uranium has to be? Spit out a number, anybody. Not quite 100%, but you're real close there. It's going to be about 90% pure for a nuclear weapon. So that's why some countries do have nuclear power, but no nuclear weapons. Just purifying it to even 90% is pretty difficult. It needs some pretty complex processes there. But specifically, I don't know how they do that. And I wish I had put a slide on how they do that. I have no idea. How do you do that? Science. And you're okay, Wyatt, no worries. Just make sure that you watch the first part of this webinar. There's a lot of stuff about buoyancy, which is really important. So, no worries. I'll put the video up after this class. Your phone died and you can't hear you? But, yeah, that's how it works. You've done submarines and you're done with them. Oh well. You get to learn more about it. So anyways, the methods that submarines do use to see are a periscope, sonar, GPS, which is a global positioning system, just like the ones in your car, and then an IGS, which is an inertial guidance system, which coincidentally is also like the ones in your car, and I'll explain how that works in a minute. Not that you drive, but you get the point. I'm going to start off with the good old periscope. It's on almost every submarine. By using mirrors cleverly, it allows people in submarines to see things above the water so they don't have to completely rise to the surface. It's literally just directly look in, see above. So, nothing too crazy there. Submarines also will use sonar, which is an acronym for sound, navigation, and ranging. So the submarine will send out a sound wave out in front of it. If this sound wave hits an object, the sound waves will reflect back to the submarine, and a computer will normally tell us, based on how long the pulse takes to return to the submarine, we can calculate the distance to the object, just based on the speed of sound in water. So the question is, how tall is a periscope? It really depends on what submarine that you are talking about. And specific number-wise, I'm not entirely sure. I'll show you a slide in just a minute here that'll show the room where a periscope would be, along with the the fin of a submarine and some sleeping quarters. I would say it's probably about, from viewing to the very top, depending against submarines, I'd say 20 feet or so. Again, it really depends. But a good question. If anyone wants to Google how tall a periscope is in certain submarines, I'd highly encourage it. So anyways, with sonar, sonar is actually based, I don't know if it's based on it, but it uses the same principles that certain animals use to see objects. Anybody have any ideas on what animals might use some sort of sonar? Sonar being just a sound wave, so maybe you're screaming and hearing an echo. There's two animals I'm looking for. One is aquatic, and one is avian-ish. It's not a bird, but it can fly. Bats are one of them. It's not quite sonar because it's in air and not in water, but bats do use echolocation, which is just high-pitched chirps reflecting off stuff around it. It can hear the voice, or hear its own voice and know where things are. And Mateo got the other one, whales. I was specifically going for dolphins, but no, whales are probably a more encompassing option. Whales and dolphins use something closer to sonar in that they use it underwater. So sonar is underwater, echolocation is in air. Same concept. Also, interestingly, aside, alright, excellent, Josiah, I'm glad you figured that out. Radar's all like that too, actually, yeah. It's just not, it doesn't use sound, it uses a like electromagnetic signal or something in air. I'm not sure specifically what kind of signal is emitted, but it's the same concept, you're right. Same idea there. I saw a question, I think. Maybe no, I didn't. Oh, interestingly, some people with impaired vision have figured out a way to use echolocation. If you just go on Google, search human echolocation, you'll find some cool articles about visually impaired people who have figured out how to use that. Very rare, but still happens. So the next thing we will talk about is GPS, just like on your phone. Global Positioning System. It's used for precise navigation of the sub. Near the sub's periscope, which is basically going to be your fin, submarines have a GPS antenna, which receives signals from several GPS satellites at the same time. So all these satellites are transmitting these signals that say maybe their position and the time of day. What the sub's antenna will do is take the data from these transmissions and determine mathematically the sub's location relative to the satellites. So it's basically like cell phone triangulation, but a little bit different. Is that why in the movies you hear that beep? I'm not sure. I think that would be sonar, actually. Because the sonar is sending out sound from one point to all sides. That's why you see that rotating line in submarine movies. But yeah, that's basically what the beep is for, just saying that's one rotation, or one revolution rather, of your sonar. So, cool stuff. That's one way to determine position. And the other way is called inertial guidance system. It's used when the submarine is really far underwater, where the GPS signals cannot reach, since the GPS signals don't handle water very well. What are you doing over there, Mateo? Anyways, the submarine's computer can use two instruments to calculate location. Accelerometers, just like the ones in your car, that can detect linear motion, so it can detect if you're going straight and how fast or back and how fast, as well as gyroscopes to detect rotational motion. So if the sub turns a little bit, the computer will know and adjust the submarine's position based on that. They do use the submarine's last known location to determine the position without any external reference. So, visual sight, audio listening stuff, satellite signals, and cool computations. Basically, that's how we do it. So, submarines about the year 1900, that's when they first started using torpedoes. But they weren't very effective. They were very primitive torpedoes in that one time a torpedo was fired, it curved back around and hit the submarine that fired it. Obviously, we've gotten a little bit better since then, that have more advanced systems, both in the torpedoes and in the submarine themselves, so that the subs will hardly ever miss their target and will never ever hit the sub that fired it. So, let's watch some cool images of destruction here. Really cool music. So, these are torpedoes, not nuclear torpedoes, just regular ones. So the way that these torpedoes detonate is by a magnetic detonator. It'll react to the ship's magnetic field. Boom. So they're not to be trifled with. They are very brutal weapons. These are big, big ships too. They're not just little ones. And note that nobody was on these ships. These are tests. So pretty brutal stuff, right? Ship is very much dead. So here's a cross-section of a submarine just to show you sort of where everything may be. This is a Victoria class, and I'll go over more class of submarines a little bit later. But it's pretty cramped in there. There's not much room for error. In fact, most of the room in a submarine is used by the reactor, if there is a reactor, in the engine room, the weapons areas, and the navigational systems. This portion right here in the center is the only part that contains the human. So submarines are very cramped. So even though it might seem cool to live in a submarine, it's cramped. There's probably not any windows, no fresh air unless you surface, and you could be underwater for months at a time. Remember, all you need is food. Maybe go up for a minute or so every once in a while. But yeah, you cannot live in those conditions. I know I couldn't. I think I would lose my mind. But like, take a look here. For scale, these are bunks. These are 6 bunks, 3 high. These are where grown men or women or whoever would sleep. This is how big the submarine is. So it's probably in more than 20 feet, because this was where the Periscope room would be. I would probably even say 30, 40 feet, depending on, or for this submarine at least. So crazy stuff here. Where do they go to the bathroom? I'm sure there's a bathroom somewhere in it. If I had to venture a guess, they probably use similar to what astronauts use in terms of reclaiming water. If you were by yourself in a furnace, it'd be cool. Yeah, but you're also probably going to be with like a million people. And by that I mean like 10, 15. And yeah, that's gross, but if you purify any waste, you wouldn't know the difference. So you probably couldn't be an astronaut then at that point either. So let's talk about some certain kinds of submarines and some cool facts about them. So the first type is called the Typhoon, or the Akula. It was built by some Russian guys called the Rubin Design Bureau. And as such, it was operated by the Soviet and then the Russian Navy. These are some of the largest subs ever built. Oh man, I meant to take a look at how big they actually were, but I didn't do that. Oops. They are nuclear subs. And what's cool about these guys is that they have multiple pressurized holes, meaning that if something punctures one hull, they can basically close some blast doors, and the rest of the submarine can survive. So if you get hit by something and you're in the right place, you won't perish. So the problem with these guys, obviously they started being in commission back in the early 1980s. When it came to about the year 2000, they started decommissioning these things because the cost of modernizing them was twice the amount of building a new kind of submarine called the Bory class. So there's no point in modernizing them because these other submarines are cheaper anyway. In Soviet Russia, a submarine make you go underwater. What? Okay. I think it does in everywhere, but yeah. So basically only 6 were ever made, only 1 still around. So the Royal Navy, which is the UK Navy, had a class of submarines called the Vanguard class, made by the Vickers Shipbuilding and Engineering Limited. It was in service in 1993, and only 4 of them were ever made. All with V names for whatever reason. Vanguard, Victorious, Vigilant, and Vengeance. I wouldn't want to mess with these guys. These are also nuclear submarines. They each carry 16 Trident missiles, which are torpedoes, and they are the UK's only nukes. So these 4 submarines each carry 16 nuclear weapons. These submarines have sort of an advanced reactor system, which makes it so, theoretically, this submarine can go around the world 40 times without resurfacing. So the question is, why do all the names start with V? I'm guessing it's because it was made by Vickers Shipbuilding. That and they are really intense names, so you can't complain. So, the United States Navy commissioned a submarine class called Virginia. So a couple things you might have heard of: General Dynamics, Northrop Grumman created this guy. This is an attack submarine, so it does also very much have missiles on it. I think I mentioned it already, it was a nuclear submarine, and it costs less than the Seawolf class of attack submarine, hence why we use it over the Seawolves. These things are pretty cutting edge. Obviously, they were made in the year 2000, so a little bit newer technology than these old guys back in the 80s. These subs have 30 planned, and these are going to be built over the next 20, 30 years. They'll be built until 2043 and used until 2060 or 2070, somewhere in between there. These guys don't actually have any periscopes. Instead, they have really high-tech cameras and other light sensors that are used instead of a periscope. And these are also built to be modifiable, so that if newer technology comes into play, it won't be a pain to replace the old technology. So, very forward-thinking of these engineers to do that for the sub. So finally we get one more really, really old submarine. I probably should change this around to make this one first. It was made in what was formerly Leningrad. Now it's called St. Petersburg, Russia. It's operated by the Soviet and Russian Navy, Soviet/Russian Navy, as well as other countries in the Eastern Bloc and other communist countries. So this is not a nuclear submarine. This is actually a diesel-electric submarine. And it was built to replace the Zulu class because the Zulu class submarines had some structural weaknesses. These are more crowded than the other subs I've shown you because they have huge batteries, since they are made with a diesel generator and not a nuclear reactor. And it moves real slow, like 2 knots. Like what? What do you mean? And while you think that thought, these are very important historical submarines. If any of you have ever heard of the Cuban Missile Crisis. Oh, structural defect. The structural defect was, there's something called harmonic vibration. If y'all seen that episode of Mythbusters where they tried to have soldiers marching on the bridge, basically what would happen, if the engines were on, it would get a certain vibration which would get really, really big and mess up the submarine or the bridge. So that's the structural defect. Sometimes these guys would just completely disintegrate. So not a very good structural bonus there. But anyways, the Cuban Missile Crisis, 4 of these guys from the Soviet Union were deployed basically to Cuba. They had nuclear missiles on them. Cuba's 90 miles away from the U.S., and we were scared about nuclear war. So, that being said, it is 7 o'clock, so it is time for class to end. If you don't have any questions, you are free to leave. If you have some questions, I'll be on for a couple more minutes. I hope you enjoyed class today. Hope you learned a lot about submarines, because I thought it was pretty darn cool myself. We do have lab in Raleigh on Saturday at 11:30 a.m. Just to remind y'all. So, thank you all very much for coming out, and I look forward to seeing you either Saturday for Raleigh and Monday for everyone else.